really.
I shouldn't say it in Mexican.
No, because I'm French, yeah.
From where were you?
From Paris. Actually, I studied in Paris 6 at the time.
Since how long were you in Mexico?
Around 20 years. Yeah.
You're Mexican.
Yeah.
Do you have a passport?
No, I could have, but I haven't did the paperwork.
Can you have double?
Yeah, yes, you can. Yeah.
So, what do you think? Wait 2 minutes?
Yeah, I think.
Okay, so welcome back everybody for the final talk of this afternoon today. So we have the pleasure now to listen to Denis Boyer about optimizing random searches, please.
Okay, thanks a lot. So first I would like to thank Sanjib, the organizer, to invite me. This is special for me. It's my first time in India, and it's quite exciting and interesting experience. So I'm going to talk about a work in collaboration with a PhD student at UNAM in Mexico City, which is now in postdoc in Chicago. And it is also a joint collaboration with Satya and Gregory. So we are mainly interested in a first passage process. For instance, consider a random process that evolves in time, and we are interested in looking at the first passage, so the time at which the process reaches for the first time a certain state or position, if it is random walk, for instance. So this kind of situation is quite relevant to understand chemical reaction kinetics or foraging animals. For instance, we may think of an animal who is searching for a food item which is located at some fixed position, or for seed dispersal, or for financial application, rescue operations, and so on. So in general, the movement of the searcher is random or stochastic, and the target is static. But there are many situations where the target itself can have an internal dynamics. For instance, it can switch between a reactive and non-reactive state, and the search can be found by the searcher only if it is found in the reactive state. Otherwise, in the non-reactive, it's like invisible to the searcher. And we are interested in situations where we have a nearly irreversible or irreversible transition from active to inactive, which means that the target will be available for a finite amount of time. And so this means that the search process will have a time constraint. And this can be relevant for some application, for instance, in gene regulation, where we can have a transcription factor who is searching for, through diffusion, a specific site on the DNA to start some transcription. But that site can be, this inhibitor may block a site nearby, which makes that the binding is impossible. So basically, the searcher has to find this target before it becomes unavailable because blocked by this guy, who may stay there for a very long time. So afterwards, then the reaction cannot happen. Or in rescue operation, for instance, these people in the submarine may have a limited amount of oxygen, and you must find them if they have a trouble before the oxygen is over. Or some in sea operations, people may only survive in the sea for a limited amount of time. Or an animal may have to search for ephemeral resources, so the fruits, for instance, which are the targets, may become rotten over time, and then so the target is no longer available. Or another setup, which is a bit similar, the search vehicle, for instance, if we are talking about rescue operation, may have a limited autonomy, so the searcher itself will not spend more time than a certain amount of time to search. Or maybe a mortal searcher as well, so the searcher may die, right? So he has to find the thing before he dies. And this is also related with other problems. For instance, simply foraging animals sometimes give up search because they don't find anything, and they move away somewhere else to try to find some other type of targets. And in resetting process, when you reset, as we heard this morning with Satya, stochastic process to the starting point, for instance. So it's like giving up the search and to start again. So except that here we do not start again, we just have one chance. So we have the first resetting and that's it, right? So basically that is the setup. So we can consider a process on the position axis here, starting from some initial position x naught. And we have a target located in the origin, which has a random lifetime tau, which is drawn from some distribution, which is known a priori. And so we see an example of successful search here, and from an example of unsuccessful search. So here I have, for illustration, represented an animal, and here, after that time, for instance, the fruit become rotten, and so it's no longer interesting or available to the animal. So they are, if we want to quantify the efficiency of the search, we can, for instance, consider several observables, like the capture probability. So what is the probability that the searcher actually finds the target before the time tau? Or how long it would take to find, if it is successful, how long it would take to find the target. So we can try to optimize this quantity, for instance. And in particular, to ask the question, so what would be the good strategy or some optimal strategy to follow in order to maximize this quantity? For instance, what is, here we have an example of Brownian motion or something like a Brownian motion, here something which looks more like a Levy flight. And we may ask how the optimal strategy may depend on the parameter of the problems, which here are simply the initial position and some lifetime distribution, for instance. So if in the Brownian limit, this problem has been studied, and it's possible to calculate the capture probability and to show that it is a function which decays exponentially with the distance. And here alpha is a mortality rate. So it assumes that the target has a lifetime which is exponentially distributed with mean 1 over alpha, and d is the coefficient, the diffusion coefficient. And the conditional mean first passage time is given by this expression. And it's very easy to see that the capture probability can be maximized to the maximum value of 1, and the conditional mean first passage time to the minimum value of 0 by taking very fast diffusion. So if you diffuse very fast, so you find early any target, even if it's a mortal target. If, for instance, if you have finite d and finite alpha and finite x naught, you can improve this probability, for instance, by resetting sometimes. In particular, if the mortality rate is small enough. So this has been proposed by a more general theory of a process that can be success or failure, and showing that sometimes resetting can improve the probability of success. So this can be the case in this situation. And also there are other groups that have studied survival probability, for instance, of a permanent target surrounded by a sea of mortal random walkers, or studied this kind of problem when we have some kind of anomalous diffusion for the searchers that can be mortal in this case, or immortal with a mortal prey. So here, what I want to talk here is about a model that so we propose to answer to the question of the optimal strategies. So we have a process which starts at x naught initial position is the initial position, and it is discrete in time. So we have basically the position, the 1D position of the walker is updated by a random displacement eta of n, where n is the number of steps or time. And these eta n are simply IID variables distributed with some distribution which is given. So we have a simple random walk, and this function has satisfied two conditions. One, it is continuous, so eta is a continuous variable, and it is symmetric. So it's an unbiased process, but the steps are not integer, so it's very different, for instance, for lattice random walk, so they are simply real length which continue that can take in principle any value. And here we have a target which is initially active, and at each time step, the target stays alive with a probability A or dies with a probability 1 minus A. So it has a lifetime of 1 divided by 1 minus A. And so this is relatively simple because it's a Markov system process for both the walker and for the target. And so I want to talk about the well-known problem without mortality. So if we take this process with a permanent target, and so a classical quantity is a so-called survival probability, which is well known in the realm of search process. So that's basically the probability that the walker starting at x naught has not crossed the origin after n steps. So we assume that when the crossing happened, so the target is found and discovered. And actually, this quantity is quite difficult to calculate in general, compared with simple diffusion, or where basically one solves the diffusion equation and applies a proper boundary condition, and it is a very relatively easy calculation. The fact that time is discrete, the solution of this problem is quite complicated, and it is expressed in these basically in these two formulas. So if we define the generating function of that quantity, which is basically the Laplace transform, discrete Laplace transform in time with respect to the variable n. So the Laplace transform of it for x naught is given by this complicated expression. So if we want to solve this problem, in principle, we have to calculate this integral and then invert in the Laplace domain, lambda, and then invert in the S domain to finally have this quantity. So it's it is very hard to do in general. So, which makes also the problem quite non-trivial and with some interesting properties. So to continue with the case of targets without mortality, so it's possible to show that the probability distribution, the survival probability decays slowly as square root 1 over square root over n, quite independently of so there is a function here which is a bit complicated, but this scaling is quite independent of the step length distribution, f, so which means that the capture probability is 1. So the searcher will, in any case, find the target after some time, even if it's a very long time. But the mean first passage time, so which is a quantity which is often used to quantify the efficiency of a search process, something that we want to minimize, here is simply given by the probability to cross the target for the first time after the n steps, and this is expected value of n, given that by that distribution probability, and it's easy to see that this is the sum of Qn, and since Qn decays slowly, too slowly, this sum does not converge. So the mean first passage time is infinite. So the diffusive strategy is not very good for finding target if we want to minimize, or at least to have something which is finite. No? And so we've heard this morning that resetting, for instance, is allows the mean first passage time to be finite. So now if we have a finite-lived target, so we can calculate this quantity that I've introduced, like the capture probability. So this is a probability that to cross the line after n step, and that the target is still alive after this amount of time. And take this simple expression here. So basically, if we want to maximize this quantity, it's like finding the minimum of that quantity. So that quantity is specifically the quantity that I've presented earlier. It is a generating function of the process without mortality, evaluated at the Laplace variable S, or the generating function variable S, equals to A, where A is a probability related to the target lifetime, right? So it's between 0 and 1. So there is a similar expression for the conditional mean first passage time. So among the trajectory that are successful, the mean time taken by this trajectory is also given by an expression which depends on that same quantity. So the thing is that we don't have that quantity directly because, as I said, it's a complicated inversion problem. So we typically, there are two possibilities. For instance, solving a simple case, or to do numerical inversions, and other analytical treatment. So for the exponential step distribution, this is an exactly solvable case. So I recall that f is the distribution of the steps. So it's a symmetric exponential distribution for the random walk steps with width 2b. And the capture probability takes this expression, and the conditional mean first passage time take this expression, which look like what we had with Brownian motion. So basically, here an optimal parameter is that B is infinite, so which will produce extremely fast diffusion, and that would be basically the fastest way to find the target. So this is kind of simple. But here we want to concentrate on Levy step distribution, so which are basically distribution which have a slow power law decay with an exponent 1 over, which are of the form 1 over eta to the power 1 plus mu, where mu is an exponent, the Levy exponent, which is between 0 and 2. And here we have a central part of the distribution, which is of order 2b. And so what we want to to address is the question how to choose the exponent which is here, or the fatness of the tail, in order to maximize, for instance, the capture probability of the mortal target by the searcher, starting at position x0. And we call it mu star cap. And similarly, we can try to independently, for instance, to minimize another quantity, which is a conditional mean first passage time, so that we want to introduce this quantity, which is the optimal exponent value for that quantity, and how it depends on the initial position and the target, well, the parameter related to the target lifetime. And these two quantities are in principle different from each other. Okay, so just a small parenthesis. Levy process has been observed widely in biological systems. For instance, here in seabirds, albatross, these are some trajectories which are obtained by tracking GPS devices that show. So here we have a little zoom of this little region which is represented here. So there are some kind of self-similar structures that appear. And these things are rather well described by Levy walks or Levy flights. And here we have similar trajectory obtained from microscopes about unicellular organisms that show quite a non-Brownian diffusion behavior. So this is active motion, which some step length distribution that look like more or less a Levy distribution. And there are many other examples in nature, like, so it has been reported for insects or for humans, for banknotes or primates, even bumblebees, etc., or even T cells. And there is a theory which has been proposed some time ago that suggests a simple model that suggests that an exponent close to 1 should be optimum for foraging. If these are predators foraging for prey, there are some arguments that show that this exponent value is a result of an evolutionary process and that seeks to optimize foraging efficiency. So here for our model, so which is simply, so which I recall is given by this. So we have an exponentially distributed lifetime, which is 1 over 1 minus a, and initial position, right? So that's the only two parameters that we have, x0 and a. And so that basically what we obtain for the optimal exponent value. So the value of 1, which corresponds to the Cauchy distribution for Levy process, does not play a particular role here, but we have many possible values for the exponent, and it depends on the initial position, the distance to the target, and the target lifetime. So on this side, we have a short-lived target. Here we have long-lived targets. And what we see, so there is a first observation, relatively remarkable observation, is that the exponent varies smoothly and then suddenly has an abrupt transition at some critical distance, fixing a parameter for the target. And for distance larger than this critical value, the optimal exponent is in the mu equal 0, simply, so which corresponds to the extremely superior diffusive case. So this is the limit of normalization of the Levy flight. And however, if the target is long-lived, so if this parameter A is relatively close to 1, so the transition becomes, so there is also an abrupt transition, which is continuous now. And these two transitions are actually separated by 3 critical points where this discontinuity vanish. vanishes. And there is a critical lifetime or critical parameter A above which, where this critical point is located, and above which the transition becomes continuous. Okay, and we have something similar for the other parameter that minimize conditional mean first passage time. Okay, so in order to understand this transition, we can plot results obtained, for instance, from either some exact numerical inversion of the Polasek-Spitzer formula, which I showed earlier, so the complicated formula in Fourier space that we have to make a Laplace inversion of that to get the generating function. So we plotted this, where we put S equals to A. And by plotting it as a function of mu, we see actually that if x naught is small enough, we have a minimum at a finite value. And after a critical, a characteristic value, a special value xm that can be calculated analytically, which is basic, so the quantity, the parameter b of the Levy distribution is set to equal to 1, the typical scale. So when the xm is equal to exponential minus the gamma function, gamma Euler constant, which is this number. Here, the slope at the origin here is 0. And above this, so when we get a little bit further away from the target side, so the position here is increasing, we have actually two minimum, and at some point, the global minimum, which is here, and the local minimum, which is here, have exactly the same value. And this is kind of coexistence point, or this is a critical transition point. And above that transition point, like the local minimum that may exist here, the global minimum is no longer a global minimum, and this is a global minimum. So this gives basically a discontinuous transition at a particular value, which is in this case 0.616, for instance. So this is say the exact numerical inversion. This is some analytical result that I will describe a little bit later. So, and this is a capture probability. So this shows that a Levy flight with this kind of exponent maximizes the capture probability, which has this behavior when we vary the distance to the target. So it's more or less linear decay. And then after this transition, it becomes constant. And the optimal exponent value is 0, which corresponds to a worker that takes extremely long jumps with relatively high probability. So this is when the target lifetime is relatively short, or the probability of dying for the target in one time step is relatively of surviving, sorry, is relatively small. But when the target, the probability of death, which is 1 minus a, is small, so the target is long-lived. So the same peak quantity basically now exhibit only one minimum, and so we pass from a situation where we have one minimum as x naught is increased, which is finite, to a situation of a monotonously increasing curve. When we pass some critical value, which is given by the same xm, which is the exponential of minus the Euler constant. And so this red curve shows the transition between this kind of behavior, non-monotonous to monotonous. All right? So in order to understand this property, we can make, for instance, an extension, some kind of Ginzburg-Landau-like expansion of the survival probability where mu plays the role of a positive order parameter, x0 is kind of a control parameter, and Q1 can change sign. So this is typically if Q2 is negative and Q1 is first negative and then positive, so we have this kind of situation. And we have a simple scenario here of first order transition when Q2 is negative, whereas we have a continuous or second order transition when Q2 is positive, like in the pictures, in the former pictures. So in the simple scenarios of first order transition, we have basically these inequalities, Q2 negative, Q3 positive, and delta, which is the magnitude of the jump, takes this value, right? And so delta goes to 0 when Q2 goes to 0, which is existence of a so if that happens, this is a tricky critical point. So if at the same time that Q1 change sign, Q2 also change sign, then we go from a first order transition to a second order transition because we have a change in curvature in the curve. But here we have actually a non-conventional scenario because it's the other way around. Assume that now Q2 is small and positive, and that Q3, the negative concavity of the curve, is given by the Q3 coefficient. So we need a fourth order term to this expansion. And if we calculate delta, so the jump as a discontinuous transition, it is given by this. And so this can be 0 only if Q2 equals 0, simultaneously Q3 is equal to 0. And this happens when this change sign. So Q1 equals 0. So if we have a two-parameter problem like x0 and a, so it's difficult to fulfill these three equations in general. That's why it's a non-conventional scenario. But in our problem, it turns out that actually Q1 and Q2 vanish at the same time and at the position x0 equal xm. So in the Polasek-Spitzer formula, actually shows that Q1 changes sign at a particular initial position, which is given by the Euler constant, so that's where it comes from. And that Q2 does not change sign, but it vanishes exactly at the same position, x0. So, which is plotted in these two figures, for instance. And this happens for any value of the survival of the target. Yeah. And
What is delta?
Delta is, so that's the jump of this first order transition. Or
So it is always the ratio Q2 by Q3 and XC?
well, here it's not the case, it's rather this expression. Because,
How do you get this delta from Q delta?
sorry?
So how do you get the delta?
So you find you take the derivative with respect to mu to find the minimum and say that evaluating the function at the minimum should be the same value at mu equals to 0. So it should be Q0, and so that gives you basically two equations. And so you can get what is the minimum, the optimal. You can find basically this solve for this guy, and then that's basically delta.
No, actually, I think maybe I missed something. What I'm confused is there's no delta in the equation. So should I take delta to be this definition you have?
No, this is a result of a calculation. This is delta is just that will be given by the shape of the curves. Okay, and it turns out that Q3 can be calculated also by a third order expansion of the Polasek-Spitzer formula, and actually it is negative as in this expected in this scenario, and change sign for a part. So here we plot it we evaluate it at the transition, and we see that that coefficient at the transition, which means when these two guys are 0, change from negative to positive at a particular value for the survival probability of the target during one step. So this parameter A, which is near, which is 0.92 something. So for the conditional mean first passage time, we can do a similar theory, and it's a little bit longer and more complicated, but in that case, one finds also a critical point with a non-conventional scenario like this one, like the previous one, and with a critical value at a slightly larger value, closer to 1.97 something. So to summarize, let's say that so this theory describes the transition in the vicinity, the optimal exponent in the vicinity of the transition. Here we show another analytical theory which works, on the contrary, quite well far away from the transition, for which all this does not work very well. So here it works well. For this other theory, it also predicts correctly the transition, although it is not very correct in the vicinity, in the details of the transition. And so this is an approximate, so these dots are based on an approximate inversion of Polazek-Spitzer formula that uses the concavity of the logarithm. So if we put an equal sign instead of inequality here and plug it, the Polazek-Spitzer formula on that side, and we can invert and get a relatively simple approximation that can be, that share some several property with the exact expansion. So, for instance, we see some the exact curve and the approximation, so they are quite good actually for very long-lived targets. And so that approximation helps to understand the non-trivial optimal exponent for finding long-lived targets. So which is the case which is closer to the standard case, which is permanent targets. So if we have, so basically if A equals to 1, so the problem is not well defined mathematically because we have an infinite mean first passage time, as I explained. And so we cannot minimize an infinite quantity. But if we have dying targets and the capture probability is nearly 1 because targets last for a very long time. So many searchers have a possibility to capture the targets. And the conditional mean first passage time turns out to be finite, so the target life is finite and can be optimized. And here, so it's given by this approximation. So this basically is optimal parameter values that we have, and which are kind of generic because they are independent of the target lifetime. What is important is that the target lifetime is very long. Nearly, we can take it going to infinity, and there is still an optimal exponent value, which is non-trivial, which is below 1 and 0, depending on the initial condition, that minimize the conditional mean first passage time, and also that maximize the capture probability. Okay, so maybe I can skip, well, there was these other results, for instance, for describing this curve, green curve here near the x not equals to 0. So, for instance, is that we start very close to the target, so the capture probability tends to a universal constant, which depends only on the target lifetime and does not depend on the distribution of steps. If we start only close enough to the target, well, we can do a first-order expansion of that and try to maximize this quantity, and actually this quantity is given by this exact expression and can be maximized. So and it can be either have a maximum at a non-trivial value, or it can be just a monotonously increasing function with a maximum at 2, which is the maximum possible value given by the central limit theorem. So which means that if we plot the optimal exponent value for a very short-lived target, it will be so the best strategy will be to follow a Gaussian random walk. And but if we start close to this target and this target becomes long-lived, it will be better to follow Levy trajectory. And if the target becomes extremely long-lived, so the exponent in this case tend to a value which is a little bit below 1, but which is not exactly the value of 1 of Cauchy. So that's the advice. If you start close to the target, move as Levy if it is long-lived, but move Gaussianly if it is short-lived. And so I would like to emphasize finally a relation with resetting process, which is a problem which was studied some time ago by Gregory, Satya, Sanjeev, and Lukas Kuzmir, which is basically the same problem, but instead of ending the search here, so the search continues by a resetting process. So you die, but you resuscitate, and you continue. So each time you die, you resuscitate, or you reset to the initial position. And you can, so this is an expression for the mean first passage time, because the target now is permanent. And there were also these discontinuous transitions that were observed. And here it was possible to have an optimization with respect to 2 parameters, the exponent of the Levy walk and the resetting rate used by the searcher. But here we have only one quantity that can be varied by the searcher, which is mu, and the searcher has no control on the lifetime of the target, and the target can have any lifetime. So the 2 problems are related, but they are different in the details. And so just to summarize, so we've seen some abrupt transition for optimal Levy flight parameters in a search problem, which a very simple search problem in 1D, with a non-conventional tricky point which separates discontinuous and continuous transition, which says that Levy search may be advantageous in ephemeral environments or in certain environments, maybe for animals or in other types of search, or rescue, etc. And we can consider several extensions, in particular other target dynamics. What happens, for instance, is the target lifetime is distributed as a power law or some other distribution. So that's about it, and thank you for your attention.
Okay, so questions or remarks? Questions, please.
So in your case, like when the target dies, it's basically this thing. But have you also tried this on-off target, like where?
Yes, yes, we have tried this. As a first step for the Brownian motion, the on-off dynamic of the target, so yeah, has been studied, and we have revisited this problem a few years ago. And it can be solved basically exactly. Yeah? So
what question is then solved exactly?
So, for instance, you can solve the probability, the survival probability of you can solve the distribution of the probability distribution of first passage time, basically, in a one semi-infinite medium or infinite medium. Yes, so in that case, and it is the problem is similar to having at long time mixed boundary conditions, so partially absorbing boundary condition.
Is the case that you're discussing here?
No, this is another
special case.
So here it's when the target dies, and then it can come up, can live again, and then dies and live again, or become visible.
That's what the question was, but
yeah.
I was just wondering whether the case when it dies forever is not a special case of that.
Yeah, it's a special case of that. But in this particular setting, it's very difficult. We have tried to do this visible, invisible dynamics and so on. It's extremely difficult because actually, yeah, it cannot be really
difficult to do what?
Close enough, because you have some kind of coupled survival probability distribution of
like
this Q tilde. That it's a Q tilde
suppose
1.
you have two
and Q
Brownian
tilde 0.
motion which turn blue and red each at random, and you're asking
what is
the probability that they cross when they are first blue, when they are blue together?
Yeah.
These questions can be done, I guess.
Yeah, but in the continuous discrete time with arbitrary step length distribution, it's extremely difficult because of it's the same kind of difficulty of inverting Polazek-Spitzer. So for the exponential, it's not. But for Levy, it's a very difficult problem.
So it's very interesting that in resetting problems, also there is a tricritical point. So in physical problems like helium-3, helium-4 mixtures, one can see these experimentally in the density coexistence plots. Yeah. So do you have like any physical significance to having a tricritical point beyond it being a continuous transition? I mean, is there something more to does it have any consequence for the resetting process?
Yeah, I mean, that's true that this problem and the resetting problem often have three critical points when we try to optimize some parameters, some optimal parameters. So the optimal parameters can have some discontinuous or continuous transition as the other parameters are varied. So there are some examples here that people here in the audience have studied three critical points in the context of resetting processes. I mean, it's kind of phenomenologically similar, but there is no close analogy with real phase transitions in condensed matter, right? But actually, we are not that much aware of a non-conventional scenario. Probably it exists when these coefficients do not have the sign that they should have. I'm not aware it in a condensed matter system, but it might exist probably.
Yeah, no, I was just curious. Yeah.
More questions? Okay, well, let's thank the speaker again. Sanjeev, there is a poster session.
Yeah. So now there's a poster session. Yeah. Maybe the participant can put the posters, and there is a reception at 7 o'clock. So from here now to 7 o'clock, basically you are free to explore the poster session. Yeah. Just here. It will be just around here. Yeah. Reception is the same place.